Hello friends, today we'll start the characterization of continuous function. So last time we have studied concept of continuous function. What is definition of continuous function? Firstly we will revise that definition and then we will go to the characterization. So a function f from metric space xd to y row is continuous at a belongs to x if family if for given epsilon greater than 0 for given epsilon greater than 0 there exists some delta greater than 0 such that d of xa less than delta whenever distance between x and a is less than delta implies distance between fx and fa is less than epsilon. This is equivalent to x belongs to s delta a implies fx lies in open sphere about f of a with radius epsilon, and then we have written this as f of s delta a is contained in s epsilon f of a. For given epsilon greater than 0, there is always some delta greater than 0 such that image of open sphere about a with radius delta is contained in epsilon open sphere about f of a, and then this is equivalent to s delta a is contained in inverse image of open sphere s epsilon f of a. Right? What again these equivalences for continuous function? Now we'll take theorem. This is first necessary and sufficient condition in terms of sequential continuity. Okay. So let xd and y row be metric spaces. xd and y row be metric spaces, and f from x to y be function. Then f is continuous at some point at a belongs to x if and only if for given epsilon greater than 0 if and only if whenever action is sequence in x such that limit of xn is equal to x a implies limit n tends to infinity of f of xn is equal to f of a. Whatever our sequence of points in x which converges to a, then its image sequence must converge to f of a. And conversely, if whenever we have a sequence converging to a whatever sequence may be, and its image sequence converges to f of a, then f must be continuous at x naught. Okay. So proof. So firstly, necessary condition. Suppose f from x row xd to y row be continuous function is continuous at a belongs to x. This implies then for given epsilon greater than 0, there exists some delta greater than 0 such that rho of xa less than delta implies d of implies is rho of fx fa less than epsilon. This is one. Now let xn be sequence of points in x such that it converges to x. Let xn be sequence of points in x such that limit n tends to infinity of xn is equal to a. This implies is, therefore, for delta greater than 0, for any epsilon greater than 0, why I am choosing delta? D of x less than delta is given. Therefore, for delta greater than 0, there exists positive integer n naught such that d of xn a less than delta for any n greater equal n naught. From 1 and 2, okay, from 1 and 2, what will get? From 1 and 2, rho of f of xn f of a. This must be less than epsilon for any n greater equal n naught. Okay, so thus we get the condition that, thus for given epsilon greater than 0, for given epsilon greater than 0, there exists some positive integer n naught such that distance between f of xn and f of a is less than epsilon for any n greater equal n naught. Right? N greater equal n naught. And therefore, limit n tends to infinity of f of xn is equal to f of a. So one way we prove the result. Now sufficient condition. Conversely, suppose f from x to y, xd to y rho is function such that function and a belongs to x such that whenever sequence xm converges to a implies f of xn converges to f of a. Okay. What is your aim? F is continuous at A. F is continuous at A. If you assume that F is not continuous at A, okay, suppose F is not continuous at A, discontinuous at A, then for some epsilon greater than 0, and any delta greater than 0, then S delta A contain at least one x, such that f of x doesn't belongs to S epsilon f of p. Is it clear? That is, this is equivalent to mod d of xa less than delta, but rho of fx fa greater than epsilon. In particular, S 1 by n A contain action for every n belongs to n such that f of xn doesn't belongs to S epsilon f of a. Then xn is sequence of points. Xn is sequence of points in X such that d of xn x a is less than 1 by n, which tends to 0 as n tends to infinity. Therefore, limit of xn is equal to x a. But rho of f of xn f of p, this is greater or equal to epsilon for all n, and therefore limit of f of xn is not equal to f of p. Limit f of xn is not equal to f of p. One and two gives contradiction to hypothesis. 1 and 2 gives contradiction to hypothesis, right? One and two gives contradiction to hypothesis, and therefore our assumption is wrong. Our assumption is wrong. Therefore, f must be continuous at a belongs to x. Is it clear? Corollary: let xt and y row be metric spaces. Then function f from x to y, is continuous at x, on x, if and only if it is continuous at every point. And then by sequential continuous, if for every point x, whenever xn sequence converges to x implies f of x must converge to f of x. So that is our corollary. But I think it is not necessary. It is just immediate consequence of definition of continuity on whole metric space. Okay. Now, this result is useful to show that function is discontinuous at some point. What is our statement? A function f is continuous at a if and only if whenever xn is any sequence converging to a implies f of x must converge to f of a. What is negation of this? F is discontinuous at a if you are able to construct at least one sequence xn which converges to a but its image sequence is divergent. Or Equivalently, if you are able to construct two sequences which converge into A, but their image sequences converge to two different points, then in that case, by using this result, that function must be discontinuous at A. Okay, so we'll take the example. Let f from RU to RU with respect to usual matrix be function defined as f of x is equal to 1 if x is rational number. X is rational number. And it is 0 if x is irrational number. Irrational. So that f is discontinuous at each A belongs to RU. Each A belongs to R. Okay. Solution. So let A belongs to R. Now since set of rational numbers, set of rationals Q and set of irrationals Q complement are dense in RU, that is Q closure is equal to Q complement closure is equal to RU. Therefore, for A belongs to R, there exists sequence of rationals xn and sequence of irrationals yn such that limit of xn is equal to A and limit of yn is also A. One. Now f of xn is equal to xn's are rational. F of yn is equal to 0 for all n. Since xn belongs to Q and yn belongs to Q complement, and therefore limit of f of xn is equal to 1, not equal to limit n tends to infinity of f of yn, which is equal to 0. From 1 to and sufficient condition for continuous function. From 1 to and sequential continuity, f is discontinuous at A. Where A is arbitrary. Okay. And therefore, f is discontinuous at each A belongs to R. Since A is arbitrary. Now take next example. Let f from R to R, RU to RU be function defined as fx is equal to say 1 if x is a rational number and it is 1 minus x if x is irrational number. So that f is continuous only at half, so that f is continuous only at half belongs to R. Again by same criterion. So suppose f is continuous at A. Continuous at A. Now since Q and set of rationals, Q set of irrationals, Q complement are dense in RU, therefore there exists sequence of rationals xn and sequence of irrationals yn, such that limit of xn is equal to limit of yn is equal to A. Is it clear? 1. And therefore limit n tends to infinity of f of xn is equal to limit n tends to infinity of f of yn 1. Since f is continuous at A, okay, by using sequential continuity we will get this. But what is image of f of xn? Xn's are rational number. So we will get limit n tends to infinity of f of xn is just 1, and here we will get limit n tends to infinity of f of yn is nothing but 1 minus yn by definition of f. Now 1 is constant sequence, 1 1 1 1, it converges to 1 is equal to yn converges to A, so we'll get 1 minus A here. So by 1. By taking A and 1 on that side, we will get A equal to 0. So A is only continuous at 0 here. A is only continuous at 0. Is it clear? Instead of this 1 minus x, if I take x minus 1, then we will get half. Okay. And therefore f is continuous only at 0 belongs to R. Is it clear? Here if I take say fx is 0, if x is next example number 3, and here if I take say x square minus 5x plus 6, x is irrational number, so that if it's continuous only at 2 3 belongs to Ru. If you assume that f is continuous at A belongs to Ru, again on same line we will get this. Here I will get 0, here I'll get f of yn. If yns are irrational number, then what we'll get here? Yn square minus 5 times yn plus 6, right? So 0 is equal to, we'll get this to be yn sequence converges to a, so we'll get a square minus 5a plus 6, and after solving we'll get a equal to 2 3. Okay, so that function is continuous only at 2 3 belongs to Ru. Now we know that every nth degree polynomial has at most n real roots. At most n real roots. Every polynomial equation with real coefficient has at most n real roots. By using that, if I take here polynomial nth degree polynomial, then I can construct the function which is continuous only at most n real numbers. At most n real numbers. Okay? Using this, note. Using this, it is possible to construct function f from Ru to Ru, which is continuous at exactly n real numbers. Okay. What would be example? Example, let f from Ru to Ru be defined as fx is equal to, say, x minus a1 into x minus a2 and so on, x minus an. X is rational number and is equal to 0 if x is irrational. So that if it's continuous only at a1, a2 dotted up to an belongs to Ru. a1, a2, ans are real number. Now if I take next example, let f from, say, Ru to Ru is defined as fx is equal to sine of 1 by x not equal to 0, and it is 0 if x is equal to 0. For real function, we know that if x not equal to 0, rational function 1 by x is continuous except 0. We know that sin x is continuous everywhere. Composition of continuous function is continuous. And therefore, sin 1 by x must be continuous except x equal to 0. Except x is equal to 0. Problem is at only 0. Okay. So that f is discontinuous only at 0. Only at 0. So solution, for x not equal to 0, 1 by x is continuous. and sin x is continuous on R implies fx is equal to sin of 1 by x is continuous on R minus 0. Okay. At 0, if I are able to construct sequences which converges to 0, but their image sequence converges to different point. So here we have sin 1 by x function. So we'll take some sequence such that which converges to 0, but its image sequence doesn't converge to f of 0. Okay. So here we know that sin 2n minus 1 pi by 2. Sin 2n minus 1 pi by 2 is minus 1 raised to n. Sin pi by 2 is 1, sin 3 pi by 2 is minus 1, and so on. Okay. We know it. Okay. So at 0, so there exists sequence xn is equal to 1 upon 2n minus 1 pi by 2 in Ru such that limit of xn is equal to limit n tends to infinity of 1 upon 2n minus 1 pi by 2. This must be 0. Now limit n tends to infinity of, now f of xn is equal to sin of 2n minus 1 pi by 2, which is nothing but minus 1 raised to n. If I put n equal to 1, then we will get sin pi by 2. So it is minus 1 raised to n minus 1. Is nothing but 1 minus 1, 1 minus 1, and so on. It's a divergent sequence in Ru because it has two subsequences x2n, f of x2n, which converges to 1, and f of x2n minus 1. Sorry, f of x2n minus 1 is 1, and f of x2n is minus 1. So this is divergent sequence. So from 1 to and sequential continuity. F is discontinuous at 0. So this is A, this is B. From A and B result hold. So to prove function is discontinuous at some point, this sequential continuity criteria is very useful that we have studied in this session. Thanks for listening lecture carefully. Bye bye.